Hi, and welcome to the lesson on tree fundamentals. This is lesson 6 of the series. Now let's talk about tree fundamentals. What exactly is a tree data structure? It is a hierarchical data structure where each node is connected by edges. It starts from a single root and branches into child nodes. Before diving deep, let's firstly understand the tree terminology that's there. Firstly, a node. It is the fundamental unit of a tree which contains the data. Edge is the connection between two nodes. Root is the topmost node in a tree. The parent and the child. A node connected directly above is the parent, and the ones below it are its children. A leaf is a node with no children. The height of the tree is the length of the longest part from the root to a leaf. The depth of node is the distance from the root to the node. Subtree is a tree formed by a node and its descendants. Now, let's look at this in action. Now, let's look at tree terminology. Let me use the color green just because they're trees. Now, the first term that we saw is a node. So, a node in a tree is pretty similar to the way it is in the graph, and it contains data. Now, this data can be, say, numbers 1 to 100, or if you are dealing with some fruit, say this can be kiwi, it can be the name of a person. Any kind of data that is there is a node. After a node, the next is an edge. A typical tree structure looks something like this. This is what is an edge. It represents the relationship between the nodes. So node 1 and node 2 are related with this relationship, and that is represented as an edge. The topmost node in a tree is called the root node. This is where the tree starts. In this, if we look at, let's consider this part of the tree. This is the parent node. This is the child node. Even here, if we look at this, the parent node is going to remain the same, and this becomes the child. But if we look at this part, this in this case is the parent, and this is the child. So this same node in this relation is the parent, whereas in the previous relation was the child. So that is how the parent and child relationship in a tree is seen. Let's redraw the tree once again for the remaining terminologies. This is N1, N2, N3, N4, and N5. In this tree, this is a leaf node. This is also a leaf node, and this is also a leaf node. Since there are no children to these nodes, they're called as leaf nodes. Now, if you see, these are called levels of a tree. This is called the height of a tree. The depth of node is for example, for this, the depth of node is the distance from the root node to this node. And a subtree is like this. It is a tree formed by the node and its descendants. Now that we know the terminologies of tree, let's look at the types of trees. The first is the general tree. Each node can have any number of children. Binary tree. Each node has at most 2 children, a left and a right. Binary search tree has a property that the left subtree contains nodes with smaller values and the right subtree contains nodes with larger values. The next type of tree is n-ary tree. Now, each node can have up to n children. Example, ternary trees, 3 children, quaternary trees, 4 children. There are also a few specialized trees like AVL, which is a self-balancing binary search tree. A red-black tree is a binary search tree with balancing rules for maintaining efficiency, and B trees, which are optimized for storage systems like databases and file systems. Let's look at a few tree properties. Firstly, the recursive structure. A tree can be defined recursively. A node with subtrees acts as children. The number of edges. For a tree with n nodes, the number of edges is n minus 1. There are two traversal methods, the depth first search and the breadth first search. In depth first search, we have pre-order, in-order, and post-order. In breadth first search, we have level order traversals. Balance. A tree is balanced if the height difference between the left and the right subtree is minimal. Basic operations on trees. First is insertion, adding a new node at the correct position. In case of BSTs, the exact position of a new node matters because the elements on the right are lower in value and the elements on the left child are higher in value. Deletion, removing a node while maintaining tree properties. Traversal, visiting nodes in a specific order, like pre-order, in-order, or post-order. Searching, finding a node with the specific value. It is especially efficient in BSTs, binary search trees. Height calculation, determining the maximum depth of a tree. Now let's look at the applications. The first is hierarchical data representation. File systems, organizational structures, XML and HTML parsing. The second is efficient searching and sorting. Binary search tree and heaps help in achieving efficient searching and sorting algorithms. Database and indexing. B trees and their variants for indexing large data sets. In AI and decision making as well, decision tree algorithms are very fundamental in developing machine learning complex algorithms. Also in game trees, like the min-max algorithm. Also in compiler design, abstract syntax trees for parsing expressions. Trees have a very varied application across different domains of computer science, and learning about trees is crucial. As we come towards the end of this lesson, let's look at a few key takeaways. Trees are foundational data structures with versatile applications. The terminology and structure provide a base for understanding advanced topics like BSTs, AVLs, and B trees. Traversal and basic operations are crucial for practical applications. Trees are integral to efficient algorithms and hierarchical data storage. That is the end of tree fundamentals. Take the quiz to test out your knowledge, and I'll see you in the next lesson.